It's that time again. We've got ourselves another riveting special topics talk to make it to. This is Making Time for Longitudinal Data, aka Time-Based Data Analysis. I'm Mark Williamson for the Biostats Core of the DaCCoTA project at the University of North Dakota. So on opening here, our fundamental goal is to explore and practice the use of time in statistical analysis. To do so, we'll look at common experimental designs that use time, looks at types of time-based analyses, look at some examples from papers for time-based analyses, then some comments on how to deal with time as a variable. Moving over, we'll practice in R as well as SAS. Wrap up with a little caveats and concerns. All right, you ready to get started? Not quite yet. Please take a moment to take our pretest before you jump right in. So, how are experiments designed with time in mind? Here are the most common setups. Starting out with the most basic, the pre-post test format. This could also be called before and after, etc. However you slice it, there are 2 time points. Now, some considerations additionally lay open. First, you can have them set up with or without the same individuals. So there is one set of individuals for the before and another set after. Or you can have the same individuals, they're measured before and after. I'm showing a line to denote there's a relationship between these groups, so they're the same individuals in this case. Now you can also have with or without control. So with a control here, now these are in red and you have some sort of treatment, you can look before and after and look at the difference. Now they could be without individuals as here, adding that on, or you can have individuals here. And a lot of these will break down analogously to things like paired t-test or test of mean differences. Next, for more than just 2 time points, there is repeated cross-sectional data. Kind of looks like this. Similar to this, but with individuals repeated across time, so multiple observations that is, there is longitudinal cohort data, which looks like this. You can see here they're kind of similar to the pre-post test, but extended out to however many time points you want. Repeated cross sections, there's going to be a different group of people at each cross section, as it were, of the population. Whereas longitudinal, they have the connected lines to show that at the baseline, these were measured from one group, and it's the same group moving forward. You can have a control and a treatment. Obviously, you can have more than 2 groups. I just had 2 for simplicity. Lastly, there is time series data, which looks more like this, which really involves usually many time intervals, is often cyclical in nature, going up and down, and can be used not so much in epidemiological data, but more for forecast, financing, weather, anything with natural cycles. They're not specifically cycles, but that's where you see it the most. Anyways, getting on to what actual statistical types are used, that statistical tests are used for time-based data. Let's dig into this. The 2 standard ones to start out are repeated measures ANOVA, which looks at differences across time periods, where the time periods are considered as categorical variables. So ANOVA is sort of an extension of a t-test. Repeated measures ANOVA is an extension of sort of the pre-post test with repeated measures. Now, similar to this is mixed models. However, again, it's different against time periods. So here's an example here. But time is more properly construed as numerical. So rather than categories, they're numbers. And mixed models are pretty flexible. They can use time as categorical. So in a certain sense, repeated measures ANOVA is sort of a special case of the mixed models, but conceptually it's easier to sort of separate these out. Think of mixed models as numerical time and ANOVA as categorical time. And finally, we have time series. We're not going to go too much into analyzing it, but there are different methods, and I'll show you some references if you want to dig further. But we'll mostly be focused on the examples of repeated measures ANOVA and mixed models, because that's more commonly used in biological, epidemiological, biomedical data. So some more advanced things that deal with time. There is survival analysis, which is all about time. Generalized estimating equations, which kind of extends beyond linear models, as well as multivariate analysis. Now this and time series, I'm not going to explicitly cover here. I just brought it up, but there are topic talks and modules that the BERD Core has done that you can look at. So survival risk analysis modules 1 through 3, linear regression module 3, and then multivariate analysis module 3. This includes multivariate analysis as well as time series. So that can be found here. So those will be general link at the end of references if you want to dive into all that. No time like the present. Let's look at some examples in practice. First, from Van Dorlemalen et al. On the winter survival of bees, we see survival in the y-axis here. Over time categories, x-axis, for different treatment cohorts, these different symbols. And we see changes over time, especially on the survival here. The not treated had lower survival fractions. So just a note, my use of lines in the previous design slide to lines to show repeated measures or not lines to show not repeated measures is not used everywhere. So here, these cohorts, I believe, are the same bees across time, despite having no lines. So it just depends on the author. Okay, as in another example from Woods et al., we see mouse handling events on the y-axis across weeks, the x-axis, for location, so home cage or playground, and genotype. And we see more handling events over time for the home cage for both genotypes, though it's more pronounced in this non-wild type. And comparing between the genotypes, there are more handling events for this than wild type. And it increases across from the lowest week to the highest week as well. More examples in the mixed models mode. Holland et al. Gives neurological atrophy rates y-axis across numerical age in years x-axis for 3 groups of patients. Cognitively healthy patients are in green, mild cognitive impairment in blue, and Alzheimer's in red. What this shows is while Alzheimer's patients have initial high rates of cognitive decline, rates of decline decrease with age. So the oldest ages, you can see all here, irregardless, pretty much irrespective of impairment, have about the same rates. So a mixed model on the non-biomedical side, we have Rashid et al. Shows a generalized linear mixed model with grape plant cultivar, so cultivars here, and disease incubation times as fixed effects, and plant replicate identity as a random effect. That model set up with identity of the plant as a random effect is needed to account for the repeated measures made on individual plants and also the generalized linear part for non-normal area. So this is one of their outcomes. Is on the x-axis we have correlation between infection rate and symptom severity, so how well the actual infection of, I think this is a plant virus, matches the actual severity of the symptoms of the outward signs. And this is across 3 week categories, 8, 12, and 16. So there we go. It looks like, I'd hate to be Merlot. It looks like it just keeps getting worse, that they have higher loads and higher severity shown. Okay, finally, let's have a brief look at just a time series to showcase a biologically relevant time series. This is a actiography, so shows activity from Fawcett et al. With insomnia patients in red and control patients in blue across 24-hour period. These orange bars show that there is a significantly more activity from control patients in the morning, so the typical waking time, and more activity from insomnia patients late at night, so the normal sleeping times. Now that we've seen some examples, let's return to a broader discussion of time as a variable. I'd like to talk about a few common considerations. First, depending on how the data is collected, time may need to be converted. A day, month, year, date is rarely the best format. Day or year could be extracted as numerical, or month, or even time, like interval hours, whatever interval of time you have. Or categories like week or pre-post, before, after intervention can be constructed. Speaking of numerical or categorical, you want to keep that in mind because different analyses and designs will treat time differently. As stated before, repeated measures ANOVA is best conceptualized as treating time like a categorical variable, while mixed models treat it as a numerical. So kind of here, the regression type analysis, the mixed models, we see more time as numerical, where here more the ANOVA type with bars, we see it as categorical. So time could be up here, number, or it could be a category. So what time means for this scientific question is another consideration, and what I mean by that is time a main feature or is it a controlling factor? So are we actually interested in differences across time, making it a main feature, or are we simply wanting to control for time as a controlling factor? A similar question is whether time is a fixed or random effect. Time is usually a fixed effect on the x-axis, a change over time, but individual is often treated as a random effect to account for the repeated measures, because by treating individuals or other grouping considerations as random, the intercepts and slopes that essentially change over time can vary across individuals. You can see here this is random intercepts and slopes, this is just random intercepts. They'll vary across individuals, which usually happens in real life and better captures your data. So there are 4 common considerations with time as a variable. With that, let's dive into a little R practice. I will go through 3 major exercises, look at the pre-post test format, a repeated measures ANOVA format, and a mixed effects model. So what are you waiting for? Let's check it out right now. Here we are in our studio. We'll first load our libraries, ggplot2, LME4, and dplyr. So then we'll want to create data sets. So this is, I created 3 essentially data sets, a pre-post data set for the difference between a new alarm and a control on the amount of snoozing done. And I formatted it into a couple different ways. It's the same data on data frame 1 and 2, just either wide or long. Because depending on how you're going to analyze it, wide or long data frames are easier. I also have, our next thing is a repeater measures ANOVA data set, which is looking at the amount of sleep in hours across months as categories, and then a couple different treatments, and the idea is the individual. And then a mixed model regression, which is also going to look at sleep over month, but month is now numerical and across a couple brands, and then a D is again an individual. Now, because these are drawn from random normal distributions, these will, every time you run this, these data sets will be slightly different. So to keep what I've already done, I have them already saved, so I'm just going to load them. If you want to do these yourselves, you run them here. If you want the data I'm using specifically for this example, I have the variables, the Y variables, that's the ones that are changing, replicated here that you can always use. Anyhow, going back up here, the data is already made. So let's get started with exercise 1, the pre-post test. So looking at the first example, part of the example with his no control, let's just look at the head. Again, we have ID, individuals, our alarm. So they either a control, so no new alarm clock, or a new alarm clock. And then looking at the amount of snooze in minutes before and after a certain time frame. So I did a subset of the data, so just looking at the new alarm. And if I do a box plot of that, what that looks like here is, well, let's see, kind of run that. Okay, so looks like before the snooze was up here, it looks like in the post time frame, snoozing went down a little bit with the new alarm, which is what we probably hope. But to test that actually out, we'll run a t-test, which is paired to account for the fact that we have paired data, and that was significant. Yes. So it's significantly, the new alarm clock significantly decreased snoozing from before and after, so the pre and post. Okay, and I'll just run a ggplot to make a little nicer plot if I want. A spaghetti plot, we can see for each, so each line is each individual. For the most part, individuals decrease in their snooze, though some increased or about stayed the same. So now if we want to add that control back in, we're going to use the same data but in a wide format. So we have alarm, so control and new alarm. Then we have these split out as pre-post snoozing, and then the difference, because we're actually going to look at this difference across treatment groups. So what I mean here for the box plot, we're going to look at the snooze difference to get into control, which is close to 0, where the new alarm, which had a more negative difference, which means on average the snooze decreased pre and post. We're going to run a t-test against the control and the new alarm. So this isn't paired because we're looking at the snooze differences. We've already accounted for that. We see a p-value is not less than 0.05, so there is no significant difference. While it looks like new alarm did decrease snoozing, it was not significantly different from the control, and we'll just do it again. A plot here, throw the spaghetti plot up here against control and new alarm. Now we'll take a look at repeated measures of ANOVA. So we'll look at our data set bed. This will be slightly different than snooze. We'll have ID, that's different individuals. Sleep in hours, the amount of sleep they got a night over months. There'll be month 1, 2, and 3. These are going to be categories. And then treatment, control, or a new mattress. So to make sure R doesn't think that our month is numerical where we want it to be categorical here, we're going to set it as a factor. That's another way of saying category. And to show you what I mean of what we're comparing is overall sleep across month. It looks like it's increasing over month, but let's do a test to check that. We'll use linear model, sleep as a function of month, and do a summary here. And now the overall model by the F statistic and the p-value is not significant, while it looks like month 2 and 3 compared to 1 was significantly higher, but we're going to look at the whole model first rather than into the little model, and this was not significant, so we're going to say overall there was not a significant increase. Now if we want to account for our ID, so individuals being repeated across time, we'll use limmer, and this will have a random effect set up like this, parentheses with I bar, or 1 bar ID, so whatever your random effect is. If we do a summary here. Now unfortunately, limmer doesn't natively do p-value, so you have to sort of compare to a linear model that does. Now it doesn't give you the overall F statistic, but what we do have is t-values for each of the comparisons, and these are slightly higher. So about 2.16 and 2.09. slightly higher than, sorry, where are we here? These ones. So it might be on the cusp. I can't actually tell using this test whether the overall model was significant. So we'll have to wait till actually SAS to confirm that. But what we can say here, I kind of made a nicer graph here, is while month 2 and 3 looks like higher sleep, it's pretty close, and they might be significantly higher when accounting for our random effect of individual, so repeated measures. Okay, let's roll in treatment within our analyses. So let's do another box plot. See if there's a difference between control and mattress across time. It doesn't look like mattress is increasing, or control is staying about the same, or certainly not increasing. If we run just linear model without a random effect to control for the fact that we have repeated measures across individuals, we see that especially treatment is different. So there's a difference between treatment, the control, and the mattress, and there's a difference across treatment and time. So that's great. Let's keep this number about 3 in mind with the interaction effect, because once we add in our random effect for individual, we are not going to get a p-value, so we need to compare. And this is over 3, so that was below 3. So again, it is significant. And what that means, by getting a nice GG plot, is that both the people with the mattress as opposed to the control, especially at like month 3, they had more sleep, more hours of sleep, and the hours of sleep in the mattress increased over time as well. So getting that new mattress improved sleep. Switching over to exercise 3, mixed models. This data set looks pretty similar, but now month is going to be actually numerical, and then we have brand rather than treatment, like treatment control mattress. There's 3 different brands of mattress that we're testing sleep across individuals. So just to plot that, what we're kind of looking for is there a change over 5 months? So if we just look at sleep by month alone, we find that a significant t-value with a p-value below 0.05. So keep this in mind, 3.4. If we add in our random effect using Limmer, again, 3.5, so that's still significant. And if we plot it, what we are saying is there was a significant increase in sleep across month, across our time, for everyone, irregardless of brand. But if we want to add brand in, we're going to add this statement here, month with the brand and their interaction effect. And what we see here is, though, while month is still significant, brand was not. So there was no difference in the brand of mattress. This is a very small t-value, and if we use the random effect, that t-value is still pretty small. So the mattress brand was not significant, but month still was. So there we go. And if you want to output your data to SAS, which you'll want to if you want to follow on with SAS next time, you can run this here, and obviously you'll need to use your own path files. And again, if you want to replicate the data here that I used for this specific analysis, you can use this. Now that we've got the R under our belt, we'll turn to another methodology, SAS. We're going to do the same sort of thing here. In fact, use the same data set, pre-post test, repeated measures ANOVA, and mixed effects model. Because you know what time it is? Yes, it's SAS time. Here we are in SAS. So I'm going to start by just loading those data sets of the exact same data I generated in R. We got that there. Let's jump right into exercise 1, the pre and post test. So we're going to start with no control. I just want to look at my 2 long and wide data sets to confirm. Yep, we have an ID, an alarm, time, before and after, and snooze, the minutes of snooze. We're just going to look for the control on the new alarm. So this is the long data set, and then again the wide data set we also had. So taking the long data set and then subsetting. This is how we subset it. We can subset with the where statement, where alarm equals new alarm. We're going to just do a quick plot. And again, looks like there's a decrease between before and after. And then we'll do a t-test to confirm, and we're going to pair snooze pre and snooze post. And this was significant. So we have confirmation that the new alarm post getting the new alarm decreased minutes in snoozing. Now if we want to throw the control in, so we use the data frame 2 here, the long data set, to do the pre and post. We're going to do the same thing here, the wide data frame, to look across category. Control new alarm. Looks like new alarm's a little bit less snooze, but there's so much deviation here. It doesn't look like a significant difference. And again, we'll do a t-test by class alarm. Variability, the var variable is snooze difference. And we'll do a plot after that. And this gives more than R, but the main point here is this was not significant. And I didn't separate out because it's kind of tricky to do the color it by control and treatment, but we can see here that by and large that it does sort of trend down, but there's no real difference between treatment and control. Anyways, we're going to go to our second exercise, repeated measures ANOVA. Just to remind ourselves what we're looking at here, we have our bed data set, which is an ID, that's the individuals, the amount of sleep in hours, month, and treatment, control versus mattress. So we're just going to look at month to start with. So our month is going to be 1, 2, and 3. And to make sure SAS knows that our month is going to be a category, we're going to use this class statement of month, and then our model is sleep as a function of month. What we find here, not including our repeated measures, so just doing a linear model, this was not quite significant as we saw in R, but the real money maker here is when we're adding in our ID as a random effect. So how to do that, we have this random statement ID. This will take into account that our ID is the different individual people across month, and then we're going to output that result. But what we see here is, while just like in R, looks like there's significant difference across at least 1 month, the overall model remained not significant. It was better than not accounting for ID, but it's still just above 0.05. So we have to conclude that there was no significant difference across month, even while accounting for repeated measures. And if we just do a little sad SG plot, you can see that there's no significant difference. Okay, why don't we add in treatment to our month here? So we're going to use VBox, Glimix. So Glimix is our generalized linear model. You could do procreg2, but this is if you just had no random effects, but I'm just using Glimix for everything. So anyways, we see here, these are treatment in blue, or sorry, control in blue and treatment in blue. It does look like mattress improves, the mattress improves sleep. And when we run the model, month, and treatment, there is a significant difference, but not month by itself. And if we factor in random effects of ID and output everything here, what we find is, yeah, the big part here is that month increased, but for the mattress from 1, 2, and to 3, and then the mattress is better than control in the amount of sleep. Sliding along to our last one, mixed models. We're going to get a print and just do a quick plot. And our data set is ID, sleep, month, and brand. One month is numerical, brand is our additional category. It looks like sleep might be increasing by month. Let's do a simple model here and plot it by month alone, not looking at brand yet. And looks like month was significant, so yeah, there was a significant increase. If we throw brand in here by having our, or actually before brand, let's throw in our random effect of ID, and that remains significant. So even accounting for ID, the repeated measures, and then let's do month and brand, both the simple model, which shows that while month is still significant, brand is not. Even accounting for different individuals, brand is still not significant, but month is. And the interaction between month and brand, more importantly, is not. All right, there you have it. That is SAS. Whew. Done with code examples and on to caveats and concerns. Number 1, if there are no repeated observations, time can usually be treated as any other type of variable. That is, for repeated measures ANOVA, if you don't actually have repeated measures, you can downgrade it to a simple two-way ANOVA where time is one category and or factor, and say your grouping is like a treatment, control, whatever is your other factor. And then mixed models could be downgraded to linear models, assuming it's normally distributed and you can use normal distribution. Okay, second, time categories should be evenly spaced. Otherwise, interpretation of differences is less clear. So for example, if you have month 1, 2, 3, and then 6, the difference between 2 and 3 and 3 and 6 is not the same interval. So that needs to be mindful. 3, data is rarely continuous. So you should interpret it as a strictly continuous variable, so taking on any value, even in decimal values, only gets you so far. If you really didn't have things like that, if you only did like month 1, 2, 3, 4, 5, that's not strictly continuous. It's numerical, but again, not continuous. So keep that in mind. And then 4, well, missing data is common in longitudinal data sets. So not all observations might have measurements at time. People may drop out, die, otherwise can't be contacted. So you have to account for that missing data. That is a common and rather large problem in longitudinal data. So you need to take that into account for your analyses. And there are more specialized and nuanced ways to do that that I'm not covering in this broad overview here. So with that, time is a concern for us all. But you know what? I believe in you. I believe in you. In conclusion, time can be a tricky subject. It often rears its head in pre-post tests, longitudinal cohort studies, and repeated cross-sectional studies. But never fear. Repeated measures ANOVA and mixed models are solid tools to deal with it. And if you want to research deeper, open up a book or other learning materials for things like time series and everything else time related. You can research deeper. I've included references at the end, but before any of that, please take the post-test and survey. That help us out quite a bit. Those aforementioned references, I'm going to highlight specifically the more biostats resources. We have things on survival analysis, multivariate analysis, regression, things that also involve time if you want to dive in here, as well as journal articles and different references. With that, I would like to, as always, acknowledge the DaCCoTA. Please cite us if you found this useful. You can use this sort of language here. And thank you. And don't let time get away from you. Have a great day.